When it comes to tactile sensor on robotic fingers, how good is good enough? How many sensors do you need and where do you put them? What is the trade-off between expensive but accurate sensors and cheap but noisy sensors? More generally, how do sensor quality affect task performance? In our paper modeling the effect of contact sensor resolution on grasp success, we present a quantitative method for analyzing the effect of sensor resolution on grasp stability prediction. In a stable grasp, forces and moments exerted on the object by the fingers and the environment are at equilibrium. The parameters needed to evaluate the equilibrium are contact locations on the object, contact forces, or surface normal vectors at the contacts, friction, mass, and mass distribution. We express resolution limits for contact sensors as a range of contact locations and surface normals that cannot be disambiguated by the sensor. Grasp quality is then assessed at the limits of this range to determine whether the uncertainties caused by sensor resolution lead to uncertainty in grasp outcome prediction. Here, we illustrate our approach using a simplified two-finger 2D planar grasp of a circle and a square. If we fix one finger and move the other one around the parameter, we can determine all the configurations where the object can be stably grasped. At each configuration, the uncertainties caused by sensor resolution will lead to a range of potential stability predictions. If any of the potential predictions differs from the true one, then the prediction at this location cannot be trusted. These locations are labeled as ambiguous. As you can see on the plots here, the advantage of high sensor resolution is a reduction of the ambiguous regions, though at slightly different rate for the circle and the square. Our analysis shows that the quality of the sensors is determined not necessarily by its benchtop specs, but by their ability to provide information that is pertinent to the task, which can also be a function of the layout and hardware design in addition to the sensor specs. Even for data-driven machine learning approaches, it is still imperative to understand the quality of that information content. As you can see in the figure here, that for sensors with limited resolution, there will be a ceiling of prediction accuracy that corresponds to the size of that ambiguous region, because even the most sophisticated algorithms cannot compensate for missing signals. Our approach lays the foundation for quantitative evaluation of the utility of tactile sensors and their design. While the approach presented focused on resolution of the sensors, the same approach can be extended to analyze other aspects of tactile sensors or even other modes of sensing.